Hello guys, welcome to some applications of rational functions. So keep in mind, right, there's, I think it is the graphing rational functions. I think I gave you guys worksheet 1 recently, and that's due tonight. Tonight being November the 5th. Right, so make sure to get that done and turn it in. This worksheet doesn't actually have any application problems on it, but I figured it might be better if I do the application stuff through some kind of video format. That way you can kind of go through it at your own pace. If you have a lot of questions, you can come see me and ask them, right? And I'm going to go ahead and I'm going to do the first two. And all I want you guys to do is take notes along with me. You can also, get a copy of this worksheet out, maybe on your iPad or print it out or something and take notes along with the video. Or you can just, there's not a whole lot you need to copy down if you're doing it maybe on paper, right? We're going to be drawing most of the stuff here ourselves. So I would just follow along in some form or fashion. I would highly recommend actually taking notes and trying to engage with this because you will see application problems in the future. So they actually do have a lot of applications. So this first one is kind of an economics application. It has to do with an idea called economies of scale. So if you take an econ with the Mr. Keogh or Mr. Gray, I think there might be a new guy, right? You probably have heard of this idea, so we're going to kind of model that mathematically. So here's our function. Average cost per unit is the output. The input is units of yogurt, right? So output, input. So if I tell you how many units of yogurt I am producing, you can tell me the output, the cost per unit. Right? It's very useful to know that. So use the steps for graphing a rational function that I've shown you guys before. Right? It's the same kind of stuff we've been doing in class. Just get given cost function, label the graph appropriately. This is something that some of you guys just completely forget to do. I noticed that on the last test, a lot of you guys were just throwing points in places but not telling me where they were. Right? We got to make sure we label. The graph does not need to be drawn to scale, so as long as you're labeling where the points are, don't worry about the tick marks actually having the exact, size that they're supposed to be at. So the point is, when I look at this rational function, I see a few things. So first off, when we think about horizontal asymptotes, this is a bottom-heavy function. And I know this because, right, we have a degree equal to 1 on the bottom, and the top has a degree technically equal to 0, right? There's no x's at the top. So you look at the degree. So bottom-heavy means your horizontal asymptote is y equals 0 always if you're bottom-heavy. So let me go ahead and put that on the graph here. Something like that. Good enough? All right, what's another thing we notice? Well, we also notice we have a vertical asymptote, and this comes from the bottom, right? So we have a vertical asymptote at x equals negative 20, right? That's what makes the bottom equal to 0. So let's see, let's put negative 20 over here. And let's make a vertical asymptote. We're not too worried about what's realistic right now. We're just trying to create the graph. All right. What else can we figure out? We can also figure out the y-intercept. Right, y-intercept, you calculate what c of 0 is. Plug in 0, You get 600 over 0 plus 20, which is equal to 30. Right, so 30, let's just put that here. Make sure you label it. This is where we start our graph. And if you guys know anything at this point about rational functions, we basically know what the shape is going to look like now. So it's going to start, because I have this point, right, I know I have a piece. It's going to do this, and it's going to be in that top right quadrant. So something like that. I also know that the end behavior flips across the vertical asymptote, so you start low, and then we're going to approach the horizontal again later. When you have a bottom-heavy situation, you never cross the horizontal asymptote. Right? This is specifically for bottom-heavy. Now, if you don't believe me, right, all you have to do is take your function and see if you can find a place where it crosses. Right? What we do is we set it equal to 0. But if you solve this, you end up getting 600 equals 0, which is nonsense, right? So no cross for the horizontal asymptote. So this is my graph. I wasn't too concerned about finding a point over here just because this is a real-world scenario. And so we're not actually going to use most of this stuff over here. We're actually only going to be concerned with the stuff on the right side. So what portion of the graph is irrelevant to the problem? It would be this stuff, right? That stuff right there. So on the right side, right? Because think about it. X represents units of yogurt. And units, that means X has to be some sort of positive, greater than or equal to 0. It's the only thing that makes sense. You can't sell -2 units of yogurt. All right, so we're just going to use that right side. Let's also create a chart to represent the average cost to produce 50, 100, 1,000, and 5,000 units of yogurt. So the chart, let's make it look kind of organized here. You can make it vertical if you want. I'm going to do it horizontal here. So this is... I'll just use X and C of X. We'll call this units, and we'll call this average cost. All right, and so we're going to have 50, 100, 1,000, 5,000. All right. And so what are we going to do here? Well, I think at this point, probably best to go ahead and just rely on a calculator. So I'm going to split screen, be fancy. And we're going to just put it in. All right, C of X equals. If you do it this way, our life is going to be a lot easier. So notice we actually got that pretty good, right? It goes through 30, and then it does this sort of downward kind of sloping thing. If you define your function this way, like you actually give it a name, all you got to do now is do C parentheses, and what's the first number? 50. And it will plug that number in for you, right? So we're getting an average cost of $8.57. And then if I want 100, same thing. C parentheses 100. I get an answer of $5. Okay. C parentheses 1,000. Oh boy. I get 59 cents approximately. And let's see the last one. 5,000. Wow. Cost went down a lot. All right, so this idea that the more you produce, the lower the cost. This is the idea of economies of scale. Because essentially, your overhead typically stays roughly constant, but if you can produce more things for the same overhead, you can charge a lower price to recoup your money or to maximize your profits or whatever. Right? So your average cost can go down and you can outcompete your other competitors. So that's essentially the idea. So the function does that. The average cost lowers the more you're able to produce sort of with the same resources, basically. So that's our little chart there. You would like to order ingredients to produce units of yogurt at an average cost of $2 per unit. How many units can be produced at $2? So in this case, right, think of what the $2, is that the input or the output? The $2 would be the output, right? Or in other words, this part. So what we would do is we would set our function equal to 2. Right, so 2 equals 600 divided by x plus 20. All right, we're setting our cost function equal to 2. We're going to solve for the units. All right, so multiply both sides by x plus 20. So those will cancel. Distribute the 2. 2x plus 40 equals 600. Subtract the 40. You get 2x equals 560. Divide by 2. X equals 280. This would be units of yogurt. Bingo. Cool. What do you observe about the average cost as you produce more units of yogurt? So I actually kind of spoiled that surprise earlier. So the idea is the more we produce, the lower the average cost is. That's the idea. That's the idea. Economies of scale. If you take an econ, you should know. You should know that idea. It's very important. Anyway, let's move on to number 2. We're talking about a chemical added to a lake to remove a pollutant. All right, lots of pollution these days. Gotta stay on top of it. The cost in thousands of dollars to remove the pollutant is given by the rational equation. This. Yuck. Where X represents the percentage of pollutant. That's important. So X is a percentage of pollutants. We plug in a percent number and we get the cost. Percentage of the pollutant removed from the lake. So the idea is, X is maybe, we want X to be close to some sort of high percentage, right? Close to maybe 80% or 90%. Basically, whatever the EPA decides is optimal. Right? If the EPA says, hey, we want you to remove 80% of that pollutant, and we don't, then we get hit by a fine of some kind. If we do, though, we avoid the fine, and we get away with doing kind of the minimum, right? Because it's going to cost money to remove the pollutant. And the more we remove, the more it's going to cost. So we want to, we want the cost to be low, but we also don't want to make the EPA mad and they shut down our company. So let's first graph this cost function. So let's say 100 is out there. I notice in the bottom here, this is going to be our vertical asymptote, right? It doesn't cancel with anything, so it's not a hole. We get a nice little vertical asymptote at 100. Do we have a horizontal asymptote? This is a tricky question. Look at it carefully here. Believe it or not, we are in what I call the equals case, right? Because the degree of the top is equal to 1. The degree of the bottom is also equal to 1, right? You have an x to the power 1 here, x to the power 1 here. That's the degree. So if it's equals, my horizontal asymptote has to be at y equals the ratio of the leading coefficients. So in our case, that would be -1 on the bottom, 6.7 on top. So 6.7 divided by -1. So that'd be -6.7. I also notice that I have a 0 for my function. So keep in mind the zeros occur in the numerator, right? So when is the numerator equal to 0? That happens exactly at 0, comma 0, right? If I plug in 0, if I actually plug in 0, I get the answer 0. Or, well, I guess more specifically, right, I get 0 divided by 100, which is equal to 0. Right, so I know I have to go through this point, and I also know I have that horizontal asymptote at -6.7, -6.7, right? So we're going to draw that. So if I only have one horizontal and one vertical, and I know where a point is, then I know the graph is going to do something like this. All right, and if this part of the graph is kind of going up into, to the right and up, the end behavior is going to flip and do the opposite over here, and then it's going to kind of curve and then approach the horizontal asymptote again. Right. So just like the last problem, right, they asked which portion of the graph is actually relevant to the problem. In our case, we should ask that question too. That's going to be essentially this window as well. Right, this portion. Why do we not go past 100? Well, it's because it's impossible to remove over 100%, right? So basically, our only options are to remove some percentage in between 0 and 100, right? That's our only possibility. So this is the relevant portion, right? Real world problems, you get rid of the stuff that's not relevant, you focus on what is. So create a chart to represent the cost to remove 50%, 80%, 90%, all the way to 99. So again, same thing. X is going to be the percentage removed. And then C of X is going to be the cost. And we're going to make a little table. So 50%, 80%, 90%, 95, 99. Okay. So let's do the same sort of shindig here. Let's open up Desmos. Desmos. All right. So we have 6.7, 100. And you guys are probably so tired of that joke now. Us adults, we killed it. We killed it bad. It's just the life cycle of the meme, I guess. The Unk Army destroyed the meme. All right, so 50%, let's plug in 80, right? Let's plug in 90. Let's plug in 95. Let's plug in 99. And let's see what we're looking at. So 6.7. Wonderful. 26.8. And then we have 60.3. Then we have 127.3. 663.3. These are all in dollars. Cool. So what do we observe about the cost as we remove a greater percentage? So as we remove a greater percentage, the cost increases. And we might even be able to say something like without bound. Right? Based on the function, right? This function is going up towards infinity. The closer I get to that asymptote, the higher the cost gets, and it keeps going up. It does not stop. So in that case, we say something like without bound, or increases like towards infinity. Now, obviously, if we're running a little company, we're not going to have infinite amount of money lying around to remove all these pollutant. Obviously, all of us would love to live in a world where we can remove 100% of the pollutant or something really close to it, but it's just really pricey to do that kind of thing. So we have to maybe figure out another solution here. Your company has designated you as the program manager in charge of removing the pollutant. The EPA requires you to remove 85%. Otherwise, a $5,000 fine will be assessed to your organization each year of non-compliance. Your budget is $10,000. Can you meet the EPA's requirement? Oh, interesting. So they require us to remove 85% of the pollutant. So first off, maybe we should see what the cost would be to do that. So let's go back to Desmos. 85. So it'd be 37.97. Get that out of the way. 37.97. Okay, and let me make sure I'm not missing something. So the cost is in thousands of dollars. Ah, that's what I'm missing. I knew 37. So we should put that here too. Thousands of dollars. So if I wanted to remove 85%, essentially this corresponds to $37,970. So obviously, that's not our budget. That's we've blown past our budget. And then if we don't do this, we get a $5,000 fine to be assessed to our organization for each year of non-compliance. Can we meet the EPA's requirement? It's looking like, my friends, we cannot. We cannot. The cost is higher than our budget. And in addition to that, right, the EPA is going to slap us with a fine, $5,000 each year. So the budget will be gone in 2 years. Womp womp. Oh well, I guess our company's going under. So we're not able to satisfy the EPA, unfortunately. And I don't see any other way out of this. So that's a shame. That's a shame. So we're just throwing this chemical into a lake, and we get fined out of business. So anyway, guys, thank you for paying attention and watching, and hopefully you got a lot out of this. Looks like there's another little problem here, which I'll just go ahead and show you guys, but I don't want to make this video too long. I think I've already gone on probably for 30 minutes. So just maybe snap a picture of this. I'll go ahead and complete it on my own time and throw the key in the drive. But just make sure, as far as action items today, right, do that graphing rational functions worksheet 1. Make sure to turn it in by the end of tonight, or tonight, yeah, Wednesday. So thank y'all for watching. Hopefully that was kind of interesting, and I'll see you when we get back.